So yesterday, I reminded you of sort of the various types of forces. Should we just spend a quick second just refreshing our mind on those? Okay, so remember, you've got what I call sideways ones, right? Like so, where you may or may not have a friction force. And then you've got sort of the bird's eye view top-down ones, where forces are perpendicular to each other. And that may or may not include friction. Right? So today we're going to be looking at another type of sideways one, but this time the force is at an angle. Is that going to make it more complicated? It's going to make it one more step. Yeah, one more step. So let's, whoops, my page is out of order there. Let's just delete it. Okay, so today we're going to be able to calculate the horizontal component of an applied force and use it in F equals ma. You might want to draw that picture. I've given you like some sample questions here, which we will get to. If you want to just take notes on loosely if you can, if you want to squeeze that in the corner, really makes no difference to me. We're going to get right into the samples right away. So I've got two forces labeled here. Now, don't get confused. There isn't actually two forces. There's only one force, Fa here, and we would call this here would be FH. And what do you think the H stands for? Horizontal. It's the horizontal component of the force. When you're pulling up at an angle like this, part of the force goes into pulling it sideways, and part of the force goes into lifting it up. Exactly. I think it was Will that said yesterday you were talking. Was it yesterday you were talking about reducing friction by lifting at an angle? I think you were, right? So I haven't labeled it on here because it's really not. We're not going to deal with it yet, but just so you know, there is a component right here. What do you think its name is? Yeah, vertical component. We won't be dealing with the vertical component too much in grade 11. That's more of a grade 12 thing. It gets a little bit more complicated. But the idea is that say you've got 100 newtons pulling here, and let's say your angle is 30 degrees. Your FH, is it going to be more than 100, the same as 100, or less than 100? Less than. Is it always going to be less than, Cole?
No.
Is that your final answer?
Yes. No. Yes.
Is that your final answer on whether that's your final answer?
Yeah.
I'm confused now.
Me too.
Is it going to be less than 100?
Which one?
Is the FH always going to be less than the hypotenuse?
Yes.
When you put it that way, yeah, right? Are the sides always less than the hypotenuse?
Yes.
Yeah, because the hypotenuse is sort of defined as the longest side, right? Yeah, okay. So this number here is always going to be less than that. And what would you say about the angle? If it's a really big number, really big angle, then the FH is going to be? Smaller. So the bigger the angle, the smaller the FH, right? If the angle is 0, well then I guess the FA would be equal to, right? It'd be the same, right? So really, this is just a subset of this. Okay. Yeah, okay. So, as I was explaining, that's basically everything that I just said. I'll post it to Schoology over there if you want to write down, be my guest. In a situation like this, not all the applied force goes into accelerating the object horizontally. Only the horizontal component acts horizontally and contributes to the acceleration. The value of FH is dependent upon, that should be dependent on the applied force in the angle. And I sort of went through that with you. Yesterday when I took the grade 12s outside and we launched the rocket, and yes, you have to take grade 12 to launch the rocket.
Actually, we kind of did it like the other day.
Yeah, with Jared.
Yeah, I heard.
It was pretty good.
Yeah. Well, yesterday we launched it from one side of the football field to the other.
Oh, we didn't do that.
No. And we put a tire where we predicted where it would be, and we were within about 10 feet of that. We counted for the wind. Of course, the wind isn't a constant force, but we were actually quite surprised at how close we got. Same idea. When you project something like that, you've got a horizontal component, and you've got a vertical component of speed. So same idea there in grade 12.
How'd you get that thing to stay on something?
Oh, well, I have a secret.
We were just using manpower.
I heard.
We didn't look as strong. Just wanted to go.
Yeah. Good one. Good one, you guys. Okay, so suppose the applied force here is 100 newtons and the angle is 30 degrees above the horizontal. How do you find the FH? Well, you think back to grade 10 trigonometry. Remember that? Good times?
Oh, yeah.
Yeah, grade 10 trigonometry. I don't know if it's in the essentials, but it's certainly in the intro and pre-calc and applied. Yeah. So, do you remember all that sine, cosine, tan stuff, right? Well, cosine is adjacent over hypotenuse. That's the definition, right? And this one here is the adjacent, and this one here is the hypotenuse. The hypotenuse is always going to be the angle one, and the adjacent one is always. Is the FH always going to be adjacent? Is the FH always going to be adjacent to the angle? Pretty much yes, as long as the angle is always measured from horizontal. In the very, very, very rare occasion, they'll put the angle there, and they just do that to be a jerk. So 99.9999999, I won't say 99 repeating, but 9999999% of the time, the horizontal components can be the adjacent. So it's always going to be the cosine. So it's always going to be FH equals 100 cos 30. Or I guess if you want to write it in a formula fashion, the horizontal component is the applied force times the cosine of theta. Okay, you can take that to the bank, deposit it. FH is equal to FA cos theta. Just one more formula in your vast array of knowledge. Dylan, what do you get? Nothing. If you're ever on Cash Cab, hey, here's the deal. You guys have seen Cash Cab? If you're ever on Cash Cab, I will be your roll shutout. For anyone. I'd like to do Cash Cab here in Dauphin. Do you think that'd be fun? No. No?
Yeah.
If the angle increases to say 60 degrees, the FH decreases, right? And it's even greater, like so. The FH is minimal. And which one gets bigger? The vertical component, right? As the angle increases, less and less of the force is used to pull it sideways. So if you're trying to pull a heavy object across the floor, is it to your benefit to increase the angle, or is it should you decrease it? Well, it turns out that actually increasing it will actually reduce the friction, which makes it easier, right? So probably 45 is your best bet. I need to give you time for that. I see some people ready. Okay. I'm going to. Okay, so you've got that sheet there. Sample ones. Let's do the first one together, and then maybe I'll give you a chance to try here. Now, one of the questions you might be asking yourself is, how am I going to know when to do this? Well, there's always going to have to be what is the question?
A right triangle.
There will be a right triangle, but there has to be like some angle of some type, right? Has to be some angle of some type. So a force of 100 newtons is applied at an angle of 30 degrees above the horizontal to a 25 kilogram sled. Determine the acceleration if the surface is frictionless. So we'll start with an easy one. We'll start with frictionless. Should we draw a free body diagram? Could you do it without? Yeah. Absolutely. If you know what you're doing, is this going to help your thinking? Or at least describe your thought process? Yeah, I like it. Let's draw a picture. It'll just take a second. And 25 is our mass. Is there any friction? No. Okay, so there's our free body diagram. Do I need to worry about, I'm just going to do them in red, do I need to worry about the weight force and the normal force? Are they forces that are acting in this particular situation?
No.
They're not acting? There's no gravity?
No gravity.
We're not worrying about that right now.
Do we need to work? Is gravity part of this? Yes. Is the normal force there? Yes. But they are balanced. Do they have any effect on it?
No.
No. So, I mean, if you want to be a true perfectionist, yeah, you should have them in there if you're interested in drawing perfect free body diagrams. But really, it's just kind of cluttering it up. Is it going to affect things? No. Now, having said that, when you start to deal with friction and vertical components, you might want those in there. So for now, it's okay. Okay, let's do that backwards thinking that I showed you. Determine the acceleration. So I'm solving for A. My last one's going to be A equals. How am I going to use, how am I going to get A equals? I know the mass, right? So what is it called? F equals ma, right? And that F, what F is that? It's the net force, right? When I get the net force with the mass, I can get the acceleration. What is the net force here? Well, the net force is going to be equal to, in this case, only the horizontal component, right? There's no other sideways force acting. So follow this backwards, like the breadcrumbs here, Hansel and Gretel. How do I get FH? I just showed you. Should we write the formula? Or should I just write numbers down? Write the formula down. FA cos 30. So that's going to be 100 cos 30. Oh, I guess this should really be FA cos theta. No big deal. You get that wrong. But I'm missing the S here, aren't I? Okay. 100 cos 30. Do I have that already somewhere? 86.6, right? Now, do you need to know how to use your calculator for trig functions? Absolutely.
Problem.
Yeah. So make sure your calculator's in degrees. Some people's calculators, you go 100 cos 30 equals. Some people's calculators, you go 130 cos equals, right? And there's no way of knowing until I see your calculator. Okay, so figure that out right now. Take a second, get your calculator out, try it out, see if you can get 86.6.
I think this way, it's the exact same way.
Yeah, it's the same thing. Yep.
Okay, so I don't need
Yep.
to write it that way. I can write it
I
this way.
suppose,
and
yeah.
you
Yeah.
understand.
Yeah. Sure. Okay, so we got our horizontal component here. What's the next step? We're going to find the net force, but here the net force is the horizontal component because why? That's the only one that's acting sideways, right? So the net force is 86.6. So really there, you're just showing me that you understand there's only one force. And now what's the last one? Finding our acceleration. F net is equal to ma. So 86.6. Our mass is 25. Solve for acceleration. So 86.6 over 25.
86 over 25.
Yep. 25 kilograms, right? You guys get your envelopes there, the Mr. Tozik was here?
Yes.
we'll say 3.5. Again, notice how I've, right? Formula, equal signs lined up, spaced it out. I even put it different colors for you, right? Your final answer's in the bottom right-hand corner. Right? That's the way it should look like. Not all sort of like your junk drawer at home. All over the place. What are we going to do if friction's involved? What step's going to change? This one? This one?
Yeah.
This one? Which one? Black, red, or blue? Which step is going to change because of friction? The black one? The red one. The red one will change because will the net force be equal to the horizontal component? No. There will be friction. What's up next? What do you know? One with friction. Drop the mic. Or the camera. Or the calculator. Force of 50 newtons applied at an angle of 15 degrees above the horizontal to a sled having a mass of 30 kilos. The friction force is 5, determine the acceleration sled. How do you feel about trying this on your own?
No.
No? Not ready for it? Okay. There's your picture, right? Are the steps the same as before? Last step is acceleration. Before that, net force, and before that, horizontal component, right? Same steps. Work backwards. Horizontal component. FA cos theta. 50 cos 15. Make sure your calculator's in degrees. Find the complex numbers, I don't want that. Say again? What'd you get for a horizontal component? Yeah, 48.29, let's say 48.3. Does that seem reasonable? Well, it's got to be less than 50. 15 degrees is a small angle, so yeah, it's not going to be that much smaller. 48.3. Okay, now, on the previous question, we said that F net is equal to FH, but that's not true here because there's
Force.
friction. So the net force here is the horizontal component, and I'm going to say plus friction. Am I really going to be adding it? No, you're really adding negative friction. Look at it that way. So 48.3 minus 5. 43.3. Is the last step going to be the same?
Yeah.
Absolutely. One 1.44 meters per second squared. Here's the big daddy, the all-encompassing review one. This basically sums up everything we've done since February 1st.
It's one question.
Just one question.
Jeez.
He's not going to help you. A man is pulling his 50 kilogram stud on a 15 kilogram sled across an ice surface with a friction force of 2 newtons. The rope makes a 30-degree angle with the horizontal. He applies the 250 newton force on the rope for 3 seconds. Find the final velocity of the sled and the distance it travels in 3 seconds.
That is
Holy
something cool.
crap.
Holy! Mr. Bennett, have you gone insane? Should I maybe I should use my evil laugh? Well, you will notice that there's no parts A, B, and C here. Let's just break this down. How about we draw a picture? Okay, let's draw a picture here and then see. Let's make it a little bit simpler. You're not going to do it?
No, I'm not gonna understand.
Oh. Well, let me help. I'm here to help you understand, Craig. We got a 50 kilogram son. Okay, so the kid weighs like about 125 pounds. He's a little older. It's not a small child here.
That's like me, I said.
I was going to say that, but I thought that'd be inappropriate. But I can agree with what you said. What's the total mass of the kid and sled? 65. Okay, make sure you do that part, right? We got
You just started or you got that?
Oh my God.
we got 250 newtons applied. We've got a 30-degree angle. And we've got a friction force of 2 newtons. Okay. We want to know the final velocity of the sled and the distance it travels in 3 seconds. So like way over here, right? How far did it go and how fast is it going? Now there's 2 giant parts to this problem. Before I can get to distance and velocity, what do I have to do?
Acceleration.
Do what we did in the other questions. Because those other questions, Lane, you're absolutely right, will give me the acceleration. So this part here, this is the dynamics part, where you have to get to the acceleration. And once you get to acceleration, then you get into the kinematics part, which is the last unit. That's the way physics works. It builds. Okay, so are we going to do the steps that we just did?
Yeah.
Absolutely. Let's do those steps. Find the horizontal component. 250 post 30. Okay, there, well? You're not writing anything down there. What's going on? Oh, yeah?
I'm still getting that.
216.5.
216.5, Graham? Okay, so follow the pattern that I showed you. Next step, find the net force. That's going to be the horizontal plus the negative friction, which is minus 2.
Why are you minus 2?
Because the friction is negative, right? Opposite.
And you go.
Then you go. F net is equal to MA. Don't mess up that mass.
65?
Yep. .3.
Oh, we're not done.
Oh, we're not done. But we're halfway there. So now you've got acceleration. Acceleration, I call the F net equals MA formula the bridging formula because it bridges all the force stuff into the kinematic stuff. I should show you the Tyler Rampton flow chart of excellence.
I see.
Have you seen it? It's outstanding. Would you like a copy?
Yeah. Yeah. I know.
Okay, how do I get from acceleration to final velocity? Remember this old gem? Delta V over delta T? What does the delta V stand for?
Velocity.
Change in velocity. So my acceleration is 3.3. My delta V is what I'm solving for. What was my time?
3 seconds.
3 seconds. 9.9 is my change in my velocity. Change in my velocity. What then is my final velocity? Is it also 9.9? It is. How come? Because I started at 0. Do I have to explicitly state that? I'm going to let you slide on that one. But I need you to understand that the change in velocity is not always equal to the final velocity.
Are you ever gonna have to find, like, are you ever gonna actually have to find final velocity? Will I ever not start at 0?
Yeah, absolutely. Well, so how do you do that? You go delta V equals VF minus VI. You just, well, it'll say it has an initial speed of 3 or something, right? It'll have to say it. Okay, so what else do I have to find? I've got the final velocity of the sled. I need to know the distance. Hey, I just take 9.9 times 3, right?
No.
Why not? Because the distance formula, because you got the Bennett stare, the distance formula has what V in it? Average. Do we have the average? We do not. We have the initial. We have the final. We do not have the average. And here's the mistake that everyone always makes. So the first thing I got to do, now I don't know if I ever actually wrote this out for you, but when you, I think I did. When you have two things to find the average, what do? Add them together and divide by 2, right? So here it's just going to be 0 plus 9.9 over 2. So the average velocity is going to be like, what is it, 4.95? This is long, Mr. Panic.
This is a 6-mark question.
Oh, yeah, maybe even 7.
Not sure.
Do you see how this is a review of everything we've done up to now?
Yeah.
Wow, this is awesome. Everyone has their own definition of fun. Come on, Grant, that's so tough. About the only thing that's missing there, if this is a review of everything done, the only thing that's missing there is vector addition, maybe, right?
Did you divide those?
Times. Times, yeah. Right? Times both sides by 3. You should put a big giant star, big highlight, whatever. Exam review there. If you can do that question, you're set.
Exam.
How many marks, Wayne?
7.
If there's no picture, probably 7, yeah. Right? 6 steps, at least 6 marks, 6 or 7 marks. If you understand that, you're in good shape up to now. Right? If you don't, that's okay. Right? We've still got time to learn it. You've got this opportunity here to look at this one. This is new, this is old, right? This is a review, this part. Okay. So in the 2 sets of problems that I have, there are a few questions that are labeled horizontal or force at angle. They are number 7 and 8. Number 2, there's only 3 of them, there's not a lot of them. And I actually, if anyone needs, I actually have another set of problems to give to you right here.
Yeah,
Maybe I'll just give it to you. Yeah. These ones have the QR codes, they're already around.
Already rock?
Yeah.